single instruction. Multiple data is a class of parallel computers in Flynn's taxonomy. It describes computers with multiple processing elements that perform the same operation on multiple data points simultaneously. Thus, such machines exploit data-level parallelism, but not concurrency. There are simultaneous computations, but only a single process at a given moment. SIMD is particularly applicable to common tasks like adjusting the contrast in a digital image or adjusting the volume of digital audio. Most modern CPU designs include SIMD instructions in order to improve the performance of multimedia use. History: the first use of SIMD instructions was in vector supercomputers of the early 1970s such as the CDC Star 100 and the Texas Instruments ASC, which could operate on a vector of data with a single instruction. Vector processing was especially popularized by Cray in the 1970s and 1980s. Vector processing architectures are now considered separate from SIMD machines, based on the fact that vector machines process the vectors one word at a time through pipeline processors, whereas modern SIMD machines process all elements of the vector simultaneously. The first era of modern SIMD machines was characterized by massively parallel processing style supercomputers such as the thinking machine CM1 and CM2. These machines had many limited functionality processors that would work in parallel. For example, each of 64,000 processors in a thinking machine CM2 would execute the same instruction at the same time, allowing, for instance, multiplications on 64,000 pairs of numbers at a time. Supercomputing moved away from the SIMD approach when inexpensive scalar MIMD approaches based on commodity processors such as the Intel i860XP3 became more powerful, and interest in SIMD waned. The current era of SIMD processors grew out of the desktop computer market rather than the supercomputer market. As desktop processors became powerful enough to support real-time gaming and video processing, demand grew for this particular type of computing power, and microprocessor vendors turned to SIMD to meet the demand. Sun Microsystems introduced SIMD integer instructions in its VIS instruction set extensions in 1995, in its UltraSPARC I microprocessor. MIPS followed suit with their similar MDMX system. The first widely deployed desktop SIMD was with Intel's MMX extensions to the x86 architecture in 1996. This sparked the introduction of the much more powerful UltraVC system in the Motorola Power PCs and IBM's Power Systems. Intel responded in 1999 by introducing the all-new SSE system. Since then, there have been several extensions to the SIMD instruction sets for both architectures. All of these developments have been oriented towards support for real-time graphics, and are therefore oriented toward processing in 2, 3, or 4 dimensions, usually with vector lengths of between 2 and 16 words, depending on data type and architecture. When new SIMD architectures need to be distinguished from older ones, the newer architectures are then considered short vector architectures, as earlier SIMD and vector supercomputers had vector lengths from 64 to 64,000. A modern supercomputer is almost always a cluster of MIMD machines, each of which implements SIMD instructions. A modern desktop computer is often a multi-processor MIMD machine where each processor can execute short vector SIMD instructions. Advantages: an application that may take advantage of SIMD is one where the same value is being added to a large number of data points, a common operation in many multimedia applications. One example would be changing the brightness of an image. Each pixel of an image consists of 3 values for the brightness of the red, green and blue portions of the color. To change the brightness, the R, G and B values are read from memory, a value is added to them, and the resulting values are written back out to memory. With a SIMD processor there are 2 improvements to this process. For one, the data is understood to be in blocks, and a number of values can be loaded all at once. Instead of a series of instructions saying retrieve this pixel, now retrieve the next pixel, a SIMD processor will have a single instruction that effectively says retrieve n pixels. For a variety of reasons, This can take much less time than retrieving each pixel individually, as with traditional CPU design. Another advantage is that SIMD systems typically include only those instructions that can be applied to all of the data in one operation. In other words, if the SIMD system works by loading up 8 data points at once, the add operation being applied to the data will happen to all 8 values at the same time. Although the same is true for any superscalar processor design, the level of parallelism in a SIMD system is typically much higher. Disadvantages: not all algorithms can be vectorized easily. For example, a flow control-heavy task like code parsing may not easily benefit from SIMD. However, it is theoretically possible to vectorize comparisons and batch flow to target maximal cache optimality, though this technique will require more intermediate state. Note: batch pipeline systems are most advantageous for cache control when implemented with SIMD intrinsics, but they are not exclusive to SIMD features. Further complexity may be apparent to avoid dependence within series such as code strings, while independence is required for vectorization. It also has large register files which increases power consumption and chip area. Currently, implementing an algorithm with SIMD instructions usually requires human labor. Most compilers don't generate SIMD instructions from a typical C program, for instance. Vectorization in compilers is an active area of computer science research. Programming with particular SIMD instruction sets can involve numerous low-level challenges. SIMD may have restrictions on data alignment. Programmers familiar with one particular architecture may not expect this. Gathering data into SIMD registers and scattering it to the correct destination locations is tricky and can be inefficient. Specific instructions like rotations or 3-operand addition are not available in some SIMD instruction sets. Instruction sets are architecture-specific. Some processors lack SIMD instructions entirely, so programmers must provide non-vectorized implementations for them. The early MMX instruction set shared a register file with the floating point stack, which caused inefficiencies when mixing floating point and MMX code. However, SSE2 corrects this. Chronology: examples of SIMD supercomputers, ILLIAC4, circa 1974, ICL Distributed Array Processor, circa 1974, Burroughs Scientific Processor, circa 1976, Geometric Arithmetic Parallel Processor, from Martin Marietta, starting in 1981, continued at Lockheed Martin, then at Teranex and Silicon Optics, Massively Parallel Processor, from NASA Goddard Space Flight Center, circa 1983 to 1991, Connection Machine, Models 1 and 2, from Thinking Machines Corporation, circa 1985, MASPAR MP1 and MP2, circa 1987 to 1996, Zephyr DC Computer from Wavetracer, circa 1991, XPLOR, from PXIs, Incorporated, circa 2001. Hardware: small-scale SIMD became popular on general-purpose CPUs in the early 1990s and continued through 1997 and later with motion video instructions for alpha. SIMD instructions can be found, to one degree or another, on most CPUs, including the IBM's Altivic and SPE for PowerPC, HP's PA RISC multimedia acceleration extensions, Intel's MMX and IWMMXT, SSE, SSE2, SSE3, SSE3 and SSE4X, AMD's 3DNOW. ARC's ARC Video Subsystem, SPARC's VIS and VIS2, SUN's MAJC, ARM's Neon Technology, MIPS MDMX and MIPS 3D. The IBM, Sony, Toshiba co-developed cell processors SPU's instruction set is heavily SIMD-based. NXP, founded by Philips, developed several SIMD processors named Xetel. The Xetel has 320 16-bit processor elements especially designed for vision tasks. Modern graphics processing units are often wide SIMD implementations, capable of branches, loads, and stores on 128 or 256 bits at a time. Intel's AVX SIMD instructions now process 256 bits of data at once. Intel's Larrabee prototype microarchitecture includes more than two 512-bit SIMD registers on each of its cores, and this 512-bit SIMD capability is being continued in Intel's future many integrated core architecture. Software. SIMD instructions are widely used to process 3D graphics, although modern graphics cards with embedded SIMD have largely taken over this task from the CPU. Some systems also include permute functions that repack elements inside vectors, making them particularly useful for data processing and compression. They are also used in cryptography. The trend of general-purpose computing on GPUs may lead to wider use of SIMD in the future. Adoption of SIMD systems in personal computer software was at first slow, due to a number of problems. One was that many of the early SIMD instruction sets tended to slow overall performance of the system due to the reuse of existing floating-point registers. Other systems, like MMX and 3DNow, offered support for data types that were not interesting to a wide audience and had expensive context-switching instructions to switch between using the FPU and MMX registers. Compilers also often lacked support, requiring programmers to resort to assembly language coding. SIMD on x86 had a slow start. The introduction of 3DNow by AMD and SSE by Intel confused matters somewhat, but today the system seems to have settled down and newer compilers should result in more SIMD-enabled software. Intel and AMD now both provide optimized math libraries that use SIMD instructions, and open-source alternatives like libsimd, SIMD x86 and SLEEF have started to appear. Apple Computer had somewhat more success, even though they entered the SIMD market later than the rest. Altiv offered a rich system and can be programmed using increasingly sophisticated compilers from Motorola, IBM and GNU, therefore assembly language programming is rarely needed. Additionally, many of the systems that would benefit from SIMD were supplied by Apple itself, for example iTunes and QuickTime. However, in 2006, Apple Computers moved to Intel x86 processors. Apple's APIs and development tools were rewritten to use SSE2 and SSE3 instead of Altiv. Apple was the dominant purchaser of PowerPC chips from IBM and Freescale Semiconductor, and even though they abandoned the platform, further development of Altiv is continued in several power architecture designs from Freescale and IBM. SIMD within a register, or SWAR, is a range of techniques and tricks used for performing SIMD in general-purpose registers on hardware that doesn't provide any direct support for SIMD instructions. This can be used to exploit parallelism in certain algorithms even on hardware that does not support SIMD directly. Microsoft added SIMD to .NET in RIRJIT. Use of the libraries that implement SIMD on .NET are available in NuGet package Microsoft BCL SIMD, SIMD on the web. In 2013 John McCutcheon announced that he had created a performant interface to SIMD instruction sets for the Dart programming language, bringing the benefits of SIMD to web programs for the first time. The interface consists of two types, float32x4, for single precision floating point values. int32x4, for 32-bit integer values. Instances of these types are immutable and in optimized code are mapped directly to SIMD registers. Operations expressed in Dart typically are compiled into a single instruction with no overhead. This is similar to C and C++ intrinsics. Benchmarks for 4x4 matrix multiplication, 3D vertex transformation, and Mandelbrot set visualization show near 400% speed-up compared to scalar code written in Dart. John's work on Dart has been adopted by ECMAScript, and Intel announced at IDF 2013 that they are implementing John's specification for both V8 and SpiderMonkey. Commercial applications. Though it has generally proven difficult to find sustainable commercial applications for SIMD-only processors, one that has had some measure of success is the GAPP, which was developed by Lockheed Martin and taken to the commercial sector by their spin-off Teranex. The GAPP's recent incarnations have become a powerful tool in real-time video processing applications like conversion between various video standards and frame rates, data lacing, image noise reduction, adaptive video compression, and image enhancement. A more ubiquitous application for SIMD is found in video games. Nearly every modern video game console since 1998 has incorporated a SIMD processor somewhere in its architecture. The PlayStation 2 was unusual in that one of its vector float units could function as an autonomous DSP executing its own instructions stream, or as a coprocessor driven by ordinary CPU instructions. 3D graphics applications tend to lend themselves well to SIMD processing as they rely heavily on operations with four-dimensional vectors. Microsoft's Direct3D 9.0 now chooses at runtime processor-specific implementations of its own math operations, including the use of SIMD-capable instructions. One of the recent processors to use vector processing is the Cell processor developed by IBM in cooperation with Toshiba and Sony. It uses a number of SIMD processors and is geared towards the huge data sets required by 3D and video processing applications. A recent advancement by Xylabs was the production of an SIMD-type processor which can be used on mobile devices, such as media players and mobile phones. Larger-scale commercial SIMD processors are available from ClearSpeed Technology, Limited and Stream Processors, Incorporated. ClearSpeed's CSX600 has 96 cores each with 2 double precision floating point units while the CSX700 has 192. Stream Processors is headed by computer architect Bill Daly. Their Storm 1 processor contains 80 SIMD cores controlled by a MIPS CPU. See also, Single Program, Multiple Data, OpenCL, References. External links. SIMD architectures, cracking open the Pentium 3, short vector extensions in commercial microprocessor, article about optimizing the rendering pipeline of animated models using the Intel streaming SIMD extensions, YEPPP. Cross-platform, open source SIMD library from Georgia Tech.